Well, here we are again. This is another video on the topic of quadratics. So it's pure chapter 2.3, I've called it. So this is quite involved in terms of what we're going to do, the concepts we're going to talk about, and the activities you need to try yourself. So this might take some time for you to get your head around, but you will reap the rewards if you stick with it. Before we start properly, we do have 4 warm-up questions for you, as ever, pretty much. Sometimes there's 3, this time there's 4. Have a go at these, pause the video and try them yourself. Only when you're ready and you've tried them fully, attempt the solutions. Don't just copy down my answers. Okay, so without further ado, here is the answer to question 1. So for question 1, we have a quadratic, which has this equation involving p and q, where p and q are non-zero constants. We're told that we have solutions x equals 2 and x equals 4. It says use your knowledge of quadratic equations to show that p equals -6 and q equals 8. Well, what we should know from quadratic equations is that if it has solutions which are integers, it can be factorised. And so based on these two values here, we can deduce that in factorised form, this quadratic would be x minus 1 solution, so x minus 2, and then x minus the other solution, the other root, set equal to 0. And so we use this bit here to factorise. Then if we undo that and expand it all out, we'd get x squared minus 2x minus 4x plus 8 equals 0. And we can simplify and collect the x terms, and we get x squared minus 6x plus 8 equals 0. We can now compare this to the initial question. And so the coefficient of x was p, which we have here is -6, and the constant at the end is q, which we've proven here is 8. So therefore we can just write down, it must be that p is -6 and that q is -8. Sorry, q is 8, not -8. Why would I say such things? So that's question 1 sorted out. Question 2, sketch the graph of y equals x squared minus 6x plus 8, writing down any points of intersection with the coordinate axes. So what always helps us sketch is if we can factorise it. This does factorise quite nicely. So think of two numbers that multiply to 8, but when you add them give us -6. Those numbers would be -2 and -4. And so we can put here -2 and -4 in the brackets. And so this is going to have solutions at x equals 2 and x equals 4. In other words, it will cross the x-axis where x is 2 and x is 4. We can find out where it crosses the y-axis by just substituting in x equals 0. If x is 0, 0 squared minus 6 times 0 is 0. We just have positive 8. So it crosses the y-axis at 8. The y-axis intercept is 8. And it's a positive quadratic, so it's going to be a happy smiley face sort of parabola. So I'm just going to sketch it in my awful, awful way. I'm absolutely shocking at sketching curves with this tablet I have in front of me, but here goes nothing. Forgive me if it looks a bit rubbish. Just trying to find a diplomatic word for rubbish there. Oh dear. Never mind, I need to just live with how terrible this looks. Anyway, so that's going to be 2, and that's going to be 4. A label of the axes x and y, obviously. And over here, that's going to be y equals 8. And so that'll do for the sketch. Question 3, we need to state the equation of the line of symmetry of that graph from question 2. So I can't really bear to sketch again because, as I've said, time and time again, my sketching is awful. So I'm going to cheat here. There's the graph, but done in a proper way. So the line of symmetry. Well, any quadratic will have a line of symmetry. The important thing to note is the line of symmetry will always be halfway in between the roots. And so if we do halfway in between 2 and 4, the line is going to be a vertical line going through where x is 3. And so the line of symmetry is going to be like this. I'll just extend it so it goes through here. So that's the line of symmetry. So the line of symmetry is x equals 3. Part B, it says deduce the coordinates of a turning point of your graph. Well, the turning point just means where it's a maximum or a minimum. So the turning point in our case is here. So we've shown that x is going to be 3 at this turning point. So what we could do is just substitute in x equals 3 to the equation of a quadratic we had. So the equation of a quadratic was y equals x squared minus 6x plus 8. So this now becomes y equals 3 squared minus 6 lots of 3 plus 8. And that's going to give us 9 minus 18. 9 minus 18 is minus 9, plus 8, that's going to be minus 1. And so what we can say here is that the y-coordinate of the turning point is going to be minus 1. So we can add this in as well. So the coordinates of a turning point, which I'm just going to lazily say TP, that's going to be 3 and minus 1. Lastly, for the warm-up, question 4, we can rewrite y equals x squared minus 6x plus 8 in completed square form. So, first of all, just copy it down, like so. To complete the square, we halve the coefficient of the x. So in brackets, the x squared, we just write the x. We then write half of minus 6, which is minus 3. Square all of that. We then subtract away the square of the second term in the brackets. So minus 3 all squared is positive 9. So we subtract away that positive 9. And we have that 8 at the end, of course. So then we have x minus 3 all squared. Minus 9 plus 8, that gives us minus 1. And so if you have a look at these values here, in completed square form, it tells us the turning point. That's something we'll explore today. And so the turning point of the graph from question 3, just going back for a second, was 3 minus 1. So in completed square form, we can work out the turning point, and in factorized form, we can find the roots. And so I'm going to mention what root form is and what I call vertex form later on. So different forms of a quadratic, factorized and completed square tell us important different things about the nature of the quadratic curve. So before we go forward into the lesson, just a few worked examples to get you warmed up. So we've got 2 different graphs to sketch, and for each one we need to give the equation of a parabola, all points of intersection of coordinate axes, and the equation of a line of symmetry, and also the coordinates of any turning point. So what I'm going to do here first of all is just add in the axes, like so. And for part A, let's see if this factorizes. Well, fortunately for us, it does factorize. And so y equals x squared minus 2x minus 3, that can be rewritten as y equals x plus 1 x minus 3. And if we substitute in x equals 0, we can also find the y-axis intercept. So 0 take 3 is going to intercept the y-axis at negative 3. And from here, we can see that the roots are going to be at where x is minus 1 and where x is equal to 3. So it's going to have a root here and there, and it's going to cross the x-axis. Sorry, it's going to cross the y-axis at negative 3. And so again, forgive me if this looks a bit rubbish, but here we go. Something that looks like that. So the first root is at minus 1, so we need to label this on. This root over here is at positive 3, and the turning point is going to be halfway in between these two. So halfway in between -1 and 3, that's going to be at positive 1. So we can label in this line of symmetry here. So that's going to be at positive 1. We need to find the y coordinate of this turning point as well. So what we can do for A is we could complete the square for this one. We could either substitute in x equals 1 and see what value that gives us for y, or we could complete the square. So I think it's just good practice for us if we complete the square for this. And so, oh, before I go on as well, it does say to label the equation of a parabola. So let's just label in that this is y equals x squared minus 2x minus 3. If we complete the square on this, by the way, what we'd have is x half of -2 to give us -1, all squared, minus off this 1 squared, so minus off 1, then minus off of 3. So in completed square form, we'd have x minus 1 all squared minus 4. And so the coordinates of y at the turning point is going to be -4. So we can add this into our sketch. So this one here, that coordinate is -4. I know it's a bit off, but forgive me, should be a bit higher. And this one here, where it crosses the y-axis, is -3. There we go. So that'll do for part A. We've labelled the turning point. Well, we're going to label it now. Turning point is going to be 1, -4. We've got the roots on, and we put the y-axis intercept, which is -3. For the second one, part B, we need to work out how to deal with this one. What makes it awkward is it's a negative parabola. It's a -2 coefficient on the x squared. So what I'm going to suggest we do is we factorise out this -2 to begin with. So say y equals -2. I'll put the whole lot in big squared brackets. So we'd have x squared. If we factorise out -2 from this, that gives us a -x. And then factorise out -2 from a 4. So divide 4 by -2, that'll leave us with -2. And then, what we have in these square brackets does factorise in a more obvious way. This would factorise into x plus 1 and x minus 2. So it's going to have roots where x is -1 and where x is +2 from this second bracket. So it's going to have roots either side. And what we also need to do is work out what the y-axis intercept is. So we can work out the y-axis intercept by substituting in where x is 0. X is always 0 at the y-intercept. And so the y-intercept is going to be 4 plus 0 minus 0. So the y-intercept is going to be 4. It's going to be an unhappy parabola. That's the technical term, an unhappy parabola. I'm joking, of course, it's not the technical term. But anyway, so now we need to work out the turning point. Okay, so what I'm going to do here, I'm just going to give myself a bit more space and just erase some of this on the part A graph. So hopefully you've got down what part A is. If not, get this copied down if you need. I'm just going to erase this to give myself a bit more space. So if we complete the square on this, I'm going to just borrow this bit here so we can complete the square from this part. So let's just let it move over here. So we have -2, big squared brackets. So we can half the coefficient of this -1x. That's going to give us -1/2. Put it into brackets. Square it. we need to minus off this term all squared. A half squared is a quarter, so we minus off a quarter, and of course then minus off that 2. So if we were to expand all this out, what we'd have would be minus 2 lots of x minus a half all squared. Minus a quarter minus 2 is minus 2 and a quarter. Minus 2 and a quarter, if we times that by minus 2, it's the same as 2 and a quarter doubled. So that'd give us 4 and a half, which as an improper fraction would be 9 over 2. So this graph is going to have a maximum point, a turning point where x is equal to a half, and the y value of that is going to be 9 over 2. So I'm going to sort of slightly cheat and just put the line of symmetry in first of all. And then we know this is going to be a maximum. Where y is 9 over 2. So, dear, I hate doing this. Here goes nothing. I'm going to try and do this curve. Then down the other side. That's actually not too bad by my standards. Still pretty awful, but please forgive me. So let's add in the other things we need. So what we need here is the roots. So one root is at minus 1. The other root on the other side is at positive 2. The y-coordinate of the y-intercept is 4, so we need to just add in here that this is going to be 4. And the equation of the line of symmetry, we've just worked out from here. This is x equal to a half. I just realised I've been slightly naughty. I've not labelled the line of symmetry for part A. The line of symmetry for part A was x equals 1. So we've labelled everything there. We need to also label for part B the equation of a parabola. The equation of this one was y equals 4 plus 2x minus 2x squared. Just check we've labelled everything. We've labelled the equation of a curve. We have the roots labelled. We've got the equation of the line of symmetry. We've got the y-axis intercept, and we'll label the turning point as well, and then we'll be done. So the turning point is where x is equal to a half, and y is equal to 9 over 2. Before we move on, I'll give you a bit of a naughty treat. I'll show you how your ClassWiz calculator can work all of this out for you. The reason I've not mentioned this beforehand is because I don't want the focus of these early lessons in Year 12 to be just number bashing on a calculator. I want the focus to be on the algebraic understanding and the numerical manipulation. But when it comes to the crunch, you can use a calculator, so it's important you know how to use this as well. So if I just show you here, if you go to the calculator, press menu, scroll along until you get to equation/func, press equals. A quadratic is a form of polynomial, so press option 2. Its degree is 2, so press option 2 again. We can now type in, I'm going to use part B as an example. We can type in the parameters of the quadratic. And so first of all, type in the parameter of x squared. So this is minus 2. So type in minus 2, press equals. The coefficient of the x is positive 2, so type in 2, press equals. Then finally the constant term is 4, so press 4 and equals. Press equals again and it gives you not only the roots, so press equals. Root 1 is where x is 2, like we had. Press equals again. The second root is at minus 1, but it doesn't end there. These calculators are almost too good. If you press equals again, it tells you, look, the maximum point. So the maximum is where x is equal to a half, and press equals again, y is equal to 9 over 2. So it even tells you the turning point of a quadratic. How amazing is that? Well, I think it's amazing anyway. If you don't agree with me, you're wrong. So let's go on and do some more work. Okay, this first activity I've called quadratic matching. So this might take you a while, and this is ideally to try yourself. This video is to supplement if you get stuck or you need a bit of guidance on it. So let's just run through this quadratic matching activity. So step 1, you need to match each expanded quadratic expression in section A to the equivalent completed square form in section B. Once you've done that, you need to assign a parabola from the third section, section C, to each of the pairs you've done from part 1. You then need to write both expressions from section A and B in the two boxes on your worksheet, labelled section A and section B respectively. Now, two of these pairs will not match to a parabola at all. It's your task to sketch the parabolas for these two pairs in the empty spaces labelled graph 8 and graph 9. For section 3 as well, in each box marked with an asterisk, you need to write down the coordinates of the turning point of the graph and the roots of the quadratic, if it has any real roots at all, of course. Some of these won't have any roots at all. So just an example to get you started. Let's say you had these two cards. These would match up. If you completed the square on this one, you would end up with this here. So these are equivalent different forms of the curve. So for section A, you'd write the expanded form. Section B is this one, because this is the completed square form. You then would have to write down in the box marked an asterisk, but it's got a turning point at -3/2 and 7/4. And it's got no real roots because it doesn't intersect the x-axis. And so this one would match to this graph. You'd put section A, this one, section B, this one, and include a brief description of the turning point and the roots in the box labelled with the asterisk. So let's move forward and I'll help you out with these if you need. So here we have section A and section B. So what I'm going to suggest is we complete the square for section A, then match them to section B. Alternatively, you could expand the brackets for section B and then see what they match to with section A. So you're going to need a bit of work to do some doodles. So I've just added a box here which says doodles on it so that I can do some working out as I go. Okay, so let's have a look at these. First of all, I'm going to take the x squared plus 6x plus 5 and see what this matches to. Okay, so let's just complete the square on this. So y equals x squared plus 6x plus 5. Let's half the coefficient of the x, we get plus 3. Square it, we need to minus off this 3 squared. So then minus off 9 plus 5. We then have x plus 3 all squared minus 9 plus 5. That's going to give us overall minus 4. So this one here, where can we find a green that matches to this expression? Well, hopefully you can see, with a bit of looking around, it's this one here. So we match this one like so. So those two have matched together. So let's start again and match the next one. So y equals x squared plus 4x plus 5. This is great practice as well in its own right for completing the square. So x squared, right, and x, half this plus 4, give it a plus 2, square that, minus off 2 squared, so minus off 4, and this plus 5 at the end. So then we'd have x plus 2 all squared, minus 4 plus 5 is plus 1 overall. And so where is the green card that has this for y equals? So we're trying to match this one to a green card. So whereabouts is it now? It's this one over here. So these two match. And we've done another one. Start again. Let's try and match this third one. So y equals x squared minus 3. Well, this one actually already is a completed square. It's something squared and plus or minus a constant term. So this one actually just matches like this. Easy as peasy. Next, let's try and match this one here. X squared minus 4x plus 3. So which one does this one match to? So let's just put this over here. So we're ready to match it to something. So, complete the square on this. So y equals x squared minus 4x plus 3. X squared, put the x in. Half the minus 4, we get minus 2. Square it all. Minus 2 all squared is positive 4, so subtract off 4, then add 3. Simplify it, we then get x minus 2 all squared minus 1. So whereabouts is a card that's got x minus 2 squared minus 1? So it's actually this middle card over here. So this one now matches like so. Next up, let's try and match this card over here. So I'm going to move this one down to here and match it to a card. But which card it's going to match to, I don't know. Let's see if we can work this out together. So, complete the square on it. So write it out. Complete the square. Half minus 4 is minus 2. Square all that. Minus off the 2 squared, so minus off 4, and plus 10. So we have x minus 2 all squared. Minus 4 plus 10 is overall plus 6. So we need a card which is one of the green ones, which says y equals this. Whereabouts is one of those? Well, let's see if we can find it together. It's going to be... Where is it? If only you could help and just shout at the screen. I can't seem to find it. I'm being a bit blind. Yes, I am blind. There we go, it's this one. And so that one's matched. So, go again. This might seem tedious, but I do promise you it's great practice for completing the square. So then we're going to try and match up this one here. So the x squared plus 4x plus 4. So complete the square on this one. That gives us x plus 2 squared. Minus off the 2 squared, so minus off 4 plus 4. So this minus from the plus 4 will cancel each other, so we're just going to be left with x plus 2 all squared. So now we need to hunt for a green card with this on it, which matches to this one over here. So what we're going to have that matches with this one is going to have to be this card down here. So we're not far from being finished, and the more we do, the easier it becomes to spot the others. So next up we need to match this x squared minus 4x one. So let's try that. So complete the square on this. Y equals x squared minus 4x. So x, this minus 4x becomes a minus 2. Square it all. Then we have to minus off this minus 2 all squared. Minus 2 all squared is positive 4, so we subtract off 4. So, because there's only a few left now, it's easy to see which one it matches to. It's got to be this card here. So there we go. Next up, let's see if we can match this one. Move, move. There we go. Now let's stuck again. The amount of time I waste with these silly things. Anyway, so let's complete the square on this one here. X squared minus 4x plus 4. So, half the minus 4 gives us minus 2. Square it all. Subtract off minus 2 all squared, so subtract off 4. But then we have this plus 4 on the end, which cancels with the minus 4 we've just taken away. So we're just going to have x minus 2 all squared. And that's it. So which one does it match to? It's got to be this bottom one here. So let's move this one over, like so. Now there's only 2 more to match, and so I would complete the square on this just to make sure it does match. It's not a trick question, by the way, it will match. Okay. And as well, it's worth me showing you how to do this one, because people sometimes get a bit thrown off the scent when it's a minus term for the x squared. You can still complete the square. So start writing it down as it is. Then factorise out a minus 1 from everything. Or actually, you could just factorise out the minus 1 from the x terms. So let's just say that's x squared minus 4x with minus 12 at the end. Now we can complete the square on what's in these squared brackets. And so we're going to have x, half of minus 4 is minus 2, all squared. And then still inside of these big squared brackets, we're going to subtract away minus 2 all squared. Minus 2 multiplied by itself is positive 4, so we subtract off 4. Still with this minus 12 at the end. We can now expand out this minus 1, so we're going to have minus x minus 2 all squared. Minus 1 times by minus 4 is positive 4, then minus 12. 4 take 12 is minus 8, and we have this minus x minus 2 all squared. And so you can indeed see that this expression here is one and the same thing as this completed square form down here. And so I've got no space down here, so I'm just going to match them like so here. And so that's how you should have 9 matched up cards in yellow and green. But not yellow and green on your sheet, but I've just colour coded it so the yellow is expanded form and green is completed square form. So now we've matched up the pairs of quadratics in the expanded form and the completed square form. We now need to work out which match to which graphs. So if we have a look at this first graph, for example, what we can see here is it cuts the y-axis at a positive number and only has one solution. It's only got one place where it touches the x-axis. And so we just want to have one solution for x where it crosses the x-axis and a positive y-coordinate. And so this one here, if we have a look in these yellow and greens, it would actually be the one which has y equals x minus 2 all squared, because that's only going to have one solution when x is positive 2. There's no other graphs between graph 1 and graph 9 that matches with just one positive solution like this one does. Okay, so what we're going to do is move this one up to here to match like so. Next, in this box marked asterisk, we need to just include a bit of information about this turning point. Okay, so the turning point of this one is down here. So I can say the turning point is at 2 and 0. Also, as well, it has one root. It's got a one root where x is 2 and y is 0. So it's got one, in brackets, repeated root. We call it repeated when it's just one root. I'll explain why it's called repeated in a moment. One repeated root, x equals 2. So we matched 1 to begin with, so that's something at least. Next, graph 2. This one is the negative one. It's a negative parabola, and luckily, maybe I could have designed this activity differently to make it more difficult actually. There was only one negative parabola, and so it has to be this one. So we can match this to graph 2. Now we need to think about the turning point. Okay, so the turning point is here. and that's going to be where x is at, sorry, where the curve is at a maximum. It's going to be maximized when this squared bracket is equal to 0. So it's going to be a maximum at -8. And that's going to be a maximum where x is positive 2. When x is positive 2, we're subtracting away 0. Remember, something squared has to be positive, or at least, I suppose, I should say, it's non-negative. So this is at a maximum where it's -8 minus 0, which will happen when x is 2. So the turning point is the coordinates 2 and -8. And as you can see here, this one doesn't cross the x-axis at all. So this one has no real roots whatsoever. Now for the top row, for graph 3, we can see it's got 2 roots, both where x is a negative, and it's got a turning point where x is negative and y is negative. So what I'd suggest, actually, if I have a look at this one here and just think about expanding it for a second. We're going to do factorising. We're going to think about factorising these in the next section. But just for now, if we factorise this, we'd get a positive 1 and positive 5. So this is going to have roots at -1, -5. So this one fits this particular pattern. What I'm trying to say is, I'm matching graph 3 to this pair. These two match to this graph. So it's got roots at -5 and -1. And in completed square form, we can also see that the turning point is where x is -3 and y is -4. So we can add this in as well. So the turning point. The completed square form tells you the turning point in effect. It's this number in its minus form. So opposite to +3 is -3. And this constant at the end is the y coordinate of the turning point. And it's got roots at x equals -5 and x at -1. So we've matched 3 of these at least. Next up, graph 4, graph 5 and graph 6. Easier now because it at least matched some of these. So this one here, it has a root at 0, you can see, and another one which is positive. And so which one of these would factorise to give one bracket which would be equal to 0, where the root is? And so if you think about this one here, that would factorise into x brackets x -4. And so that's the only one that would factorise in a way where you can see that one root must be where x is 0. And so this one has got to match to graph 4. As well as that, we could have matched it by looking at the turning point, the minimum point. It's got a minimum where x is positive, in this case 2, and y is negative, in this case -4. And so we can add this information in. The turning point is at the point 2, -4, and it's got roots where x is equal to 0, and the second root would be where x is equal to 4. From this bit here I mentioned. Graph 5, it's got one repeated root. It only touches the x-axis once, where x is a negative value. So let's work out which one this must match to. The only one with a repeated root we can see here is going to be this one. This would have a repeated root where x is -2. And so this one matches here. So the turning point is where x is -2 and y is 0. And it's only got one repeated root, when x is equal to -2. Graph 6, this has got a line of symmetry along the y-axis. This is completely symmetrical and it crosses the y-axis at a negative value. And so this is like the graph of y equals x squared. That's symmetrical about the x-axis. So it's like a shift of y equals x squared, but down a certain number of units. And so it'd match to this one here. It's actually y equals x squared, but 3 units moved downwards. Okay, so it's got a turning point at -3, 0. So we can add this information into this box here. Turning point at -3, 0. And it would have 2 roots as well. And so if we rearrange this equation, we'd have x squared equals 3. Therefore x equals plus or minus root 3. So it's got roots where x is negative root 3 and where x is positive root 3. We now go on to the final row for graphs 7, 8 and 9. So we've only got these 3 left to match, and so what we can do now is first of all just add on our axes for graphs 8 and graphs 9, like so. First of all, I'd suggest we just start with graph 7 and think about this one. It has no real roots, and as you can see here, it does have a turning point where x and y are both positive. So no real roots. It would have to be this one here, because this one has a turning point where x is 2 and y is 6. This one here has no real roots either. However, this one does have a turning point where x is -2. Here x is positive, and so this one for graph 7 would have to match to these 2 here. So we can fill in about the turning point. So the turning point for this one would be where x is 2 and y is 6. So x is 2, y is 6, and it has no real roots whatsoever. Now what we can do, we can just match these to either graph 8 or graph 9. Doesn't matter which, because we're going to have to do graph 8 and graph 9 ourselves anyway, in terms of sketching them. And so, if you have a look at graph 8, as I've put it here, this is going to have a turning point where x is -2 and y is 1, just based on this green form, the completed square form of a graph. So, it's got a turning point at -2 and +1. So it's going to have a turning point somewhere here. And it's also a positively shaped quadratic because the coefficient of x squared is +1. And so it's going to have the lowest point here, and it's going to be curving upwards around it. So it's going to be something like this. Okay, so because of that, if that's its lowest point, it doesn't get lower than 1, this one also, we can say it's got no real roots. So there's a few in this activity with no real roots at all. So that turning point is at -2 and where y is +1. For graph 9, however, this one will actually factorise. And so we can think of 2 numbers that multiply together to give 3 and add up to -4. They'd be -3 and -1. So this one does have 2 roots where x is +3 and +1. And it has a turning point where x is going to be +2 and y is -1. So it's going to be something a bit like this, if I can just sketch it not too badly. That'll do. It's not the best sketch. None of my sketches ever are. So 1 and 3, and a turning point. Notice as well, the turning point is always halfway in between the roots. The turning point here is where x is 2 and y is -1. So we can add this on to this asterisk box. Turning point at 2, -1, and it's got roots at x equal to 1 and at x equal to 3. So that bit of activity is done. Might have taken a while, but it's worth doing and sticking with. Activity 2 now for you. Classifying quadratics by the number of distinct solutions. So it links into activity 1 as well. So just to explain this activity, you need to try yourselves ideally. So part 1, you need to label each parabola from the first activity with its number of distinct solutions. All this means is it's the number of times each parabola cuts the x-axis. Distinct in this sense just means different or unique relative to others of a similar type. So distinct means different routes. Part 2 of this activity, well, we'll come to part 2 in a second actually. Just to give you an example, this parabola opposite, that would have 0 distinct solutions since the curve doesn't cut the x-axis. It intersects the y-axis, but that doesn't count in terms of a route. Yeah, part 2, as I was mentioning. Each quadratic from activity 1, you need to write that under the correct heading in the following tables. It says tables below here because relative to your worksheet in front of you, it's the tables below where this is written. Factorise each quadratic as well where possible. Some of them won't, and add these to the tables. So let's get going. So first of all, let's think about the ones with 0 distinct solutions. And so here these are paired up from before. And so which one of these have 0 distinct solutions? Okay, well, if you go back to your previous page and have a look which ones didn't cross the x-axis and which equations you matched to those graphs, the first one, or one of them at least, was y equals minus x squared plus 4x minus 12. And so one of them was this one here, which had this counterpart in its completed square form. Another one which didn't match was x squared minus 4x plus 10. This one didn't match either, and had this as its completed square counterpart. And as well as that, the third one that didn't have any real roots, the third one that didn't cross the x-axis, was y equals x squared plus 4x plus 5, which had this as its completed square form. If you try to factorise these as well, you should see that none of them factorise, so just put not applicable or does not factorise. If it has no roots, you can't factorise it using real numbers. None of these factorise, so that's the ones with 0 distinct solutions matched. These with 1 distinct solution, the ones with a repeated root, the most important thing to spot here is if it's got 1 distinct solution only, the quadratic can be written as a perfect square, essentially just one thing all squared. And so one of them is this one here, because in its completed square form, it's x minus 2 all squared and nothing else. And the other one is this one, x plus 2 all squared, which is this in its expanded out form. In terms of factorising these are already factorised. Okay, it's called a repeated root, by the way, because in the longhand factorisation, it'd be y equals brackets x minus 2, then x minus 2 again. But of course, we can write that in the simpler way and just say it's x minus 2, all of that squared. Similar for this one here. It's y equals x plus 2, x plus 2, which is just the same as saying it's x plus 2, all squared. Now the third set, the ones with 2 distinct solutions, there's 4 of these. And so no particular order, we just match these any old how. Okay, so putting these in any order, really. And the final one, this x squared minus 3, like so. So this first one, this is factorised, can be factorised into y equals x plus 1, x plus 5. This second one, we can factorise an x out of each and say it's x minus 4 in the second part. This one, we factorised this previously. So this can be factorised into x minus 3 brackets x minus 1. Now, this last one is a bit of a strange one. In terms of integers or whole numbers, it doesn't factorise. But what I want to do is show you that you can think of it as being factorised in a sense. So if you include integers in terms of factorisation, we could rewrite this as y equals x plus root 3, x minus root 3. So that's one way you could think about it factorising. If you notice here, two distinct solutions mean that it can factorise into two distinct brackets. If you include the case where even the numbers aren't necessarily integers. So let's just dwell on these tables just for a moment if we can. So have a look at these. Zero distinct solutions, you can't factorise them. One distinct solution, they factorise into one particular kind of bracket. So one distinct solution, one bracket in a sense. That bracket is repeated, hence repeated root. Two distinct solutions, two distinct brackets. As well as this, the completed square form, going back to activity 1 and linking it to activity 2, that tells us essentially where the turning point is. And so just looking at these two different forms, the completed square form and the factorised form, the completed square form helps us to work out the vertex, which is another word for turning point. Factorised form, if we can factorise them, helps tell us the roots. And so this can be summarised as follows. So I always think of it, completed square form, I think of that as being vertex form. And so any quadratic can be rewritten in this format here. So a is just a multiplicative constant, okay? A is often 1. That's why you have like just 1x squared. A could be 2, 3, 4, or whatever really. So a is just some sort of multiplicative constant at the beginning. Often it's just 1. So if it's written in this form, the quadratic has a turning point at h and k. I'll just put h and k. I don't want to use the letters a, b, and c, because that could be confused with the standard form of a quadratic equation, ax squared plus bx plus c. And if the quadratic can be factorised, or if it has any roots, it can be written as a brackets x minus s brackets x minus t, if it has two roots at s and t, or if it's got a repeated root, it can be written as y equals a brackets x minus s all squared, where s is the repeated root where it just touches the x-axis. So an activity for you to try now. This is just a preamble to when we talk about how we can work out how many distinct solutions a quadratic has. So this isn't designed to be hard, it's designed to get you thinking. So first of all, part A. We can rearrange that to x squared equals 4, square root both sides. So x is either going to equal minus 2 or positive 2. Dead easy. Part B, x squared plus 6x plus 9. Well, we can factorise this. What two numbers multiply together to give 3, and when we add them, gives us 6? Well, that's positive 3, isn't it? 3 and 3. 3 times 3 is 9, and 3 add 3 is 6. So x plus 3 brackets x plus 3 equals 0. In other words, x plus 3 all squared equals 0. That's only going to equal 0 for one value of x, which is where x is negative 3. This one here, part C, we can rearrange to be an x squared equals minus 4. X will be the square root of minus 4, which we can't do. For further maths, we have imaginary numbers, but for the real numbers, there are no real solutions. You can't square root a negative value unless you're talking about further maths. I'll leave that for your further mathematics colleagues and classmates to explain to you. I'm not going to go into it here, no way. So that activity, you saw that one of them had two solutions, one of them, part A, had, no, one of them, part B, had one solution, part C had no solutions. So what defines how many solutions a quadratic has? So here's the quadratic formula, which should be well familiar to you now, where A is not 0. So which aspect of it determines the number of possible solutions to the quadratic equation? It's the expression inside the square root, which is called the discriminant. So because mathematicians can be lazy in terms of writing down, the discriminant actually has a symbol. You can call it this triangle, which is capital delta. So discriminant, triangle symbol, delta, is b squared minus 4ac. That tells you how many roots a quadratic has. If you think about it, if b squared minus 4ac is positive, then x is going to be minus b plus something over 2a, or minus b minus something over 2a. So if this is positive, it's going to have two solutions. If the discriminant is exactly equal to 0, what's going to happen there is you're just going to be left with just one solution, b over 2a, because that discriminant is going to be equal to 0, so you can just forget about it. If the discriminant is negative, you can't square root a negative. This whole equation blows up and can't be solved. So if this is positive, two solutions. If it's equal to 0, exactly one solution. If it's negative, we have no real solutions. So just to explain this graphically, here's where a is greater than 0, a happy parabola. Here's where a is less than 0, an unhappy parabola. And so if the discriminant is greater than 0, like I said, two real roots. A graph would cross the x-axis twice. If, however, you had this here, where the discriminant is equal to 0, would have one distinct repeated real root, where it just scrapes the x-axis once. If, however, the discriminant is less than 0, we have this case here, where we have no x-intercepts, in other words, no real roots whatsoever. Now I've got a couple of worked examples to do together. So this involves the discriminant. So find the values of k for which this function here has equal roots. So equal roots is just a different way the examiner might try and throw you off a percent. Equal roots, that just means one repeated root. Equal roots just means there's one repeated root. If it's a repeated root, that tells us the discriminant has to be equal to 0. So now we need to think about what our a is, what our b is, what our c is in terms of the standard form of a quadratic. So our a, coefficient of x squared, is 1. Our b is the coefficient of our x, which is just k. Our c is a constant term at the end, which is just 9. So therefore b squared, which is now k squared, minus 4 times a, which is 1, times c, which is 9, that equals 0. 4 times 1 times 9, that's 36. So k squared minus 36 must equal 0. K squared therefore is equal to 36. Therefore k is either minus 6 or positive 6. If k is minus 6 or positive 6, this equation will have one repeated root. I'll just show you what that is because it's quite quick for me to show you. If k was 6 or minus 6, we'd either have x squared plus 6x plus 9, which should be x plus 3 all squared. You see how it can be written as a perfect square? That would have root at minus 3. Or, if k were negative 6, we'd have this, which could be written as x minus 3 all squared. Again, a perfect square, that would have a root at positive 3. So that's just to show you what would happen in the case of k being minus 6 or positive 6. Question 2, we need to find the range of values of k for which this equation here has two distinct real solutions. Two distinct real solutions implies that b squared minus 4ac is greater than 0. So our a, in this case, the coefficient of x squared is 1. Our b is 4. Our c, the constant at the end, is just k. So b squared, which is 4 squared, minus 4 times a, which is 1, times c, which is k, that must be greater than 0. If we simplify this now, 4 squared is 16. 4 times 1 times k is 4k. So 16 minus 4k is greater than 0. Add 4k to both sides. That shows that 4k has to be less than 16. And finally, divide through by 4. We then now know that k has to be less than 4 for that to have two distinct real solutions. Quite a lot of work done there, so really important that you now practice these ideas yourselves. On page 30, you'll find exercise 2F. Just try question 1 of that to give you some grounding. Then move on afterwards to page 32, exercise 2G. Try all the questions in that exercise, please. If you get stuck, you know the drill. Ask a peer, a classmate, or ask me if your answers at the back don't match what you've got. And if you're still stuck or you can't reach me, send me an email or leave me a comment on this video. Thanks for listening. That was a bit of a slog to get through, but it is crucial that you understand quadratics really, really well. So once again, I'll say thank you sincerely for listening, and you'll hear from me soon. Bye for now.